Uh, can you see my slide?
Yeah, very good.
All right. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.
Waalaikumsalam warahmatullahi.
Bismillah ar-Rahman ar-Rahim. Today is the last lecture, the last one. So as I mentioned before, I divided in 3 parts. In part 1, I mentioned something about probability and graph and combine all together and introduce algebraic graphs. In part 2, I had some introducing spectra graph theory, and first I introduced some matrices associated to a group, and then define a spectra for each of them. In the last part, in the previous part, I introduced 3 topological indexes and gave some examples in algebraic graphs. As far as I know, I introduced the winner index, first and the second Zagreb index, and second index. Now I'm going to continue introducing topological indexes. So I start with number 4, which is Hosoya index. So I'm introducing Hosoya index. The name Hosoya comes from Professor Hosoya, who is Japanese chemist. He's not mathematics, he's basically chemist, and this index actually coming from chemistry. He introduced in 1970 years, is more than, it's about 15 years ago. Let me give the definition. So suppose that gamma is a graph and we have a vertex set consisting n vertices, v1, v2, vn, and h set e1, e2, ef. So we have n vertices and m edges. A matching for a graph is a subset M of edges. So we have some edges in a set with this property that any 2 arbitrary edges in subset M has no intersection. So this is the definition of a matching number. Let me give an example. Suppose that gamma is the following graph. So we have 4 vertices, v1, v2, v3, and v4, and we have 5 edges. E1 is edge between v1 and v2, e2 is an edge between v1, v3, and e3 edge between v1, v4, e4 is an edge between v2, v3, and e5 is an edge between vertices v3 and v4. Now, let me give matching sets with different size. Now, let me start with size 1. So the matching set with size 1 is empty set, because if you take empty set, so everything is is clear and every condition is satisfying for empty. So we have one matching of size 0. Now, how about size 1? If you take any of a singleton set consisting an age is a matching set of size 1, because if you take, for example, the set consisting an age E1, so the condition is whole, because the condition is that if we have some ages in a set, we should have this property that any of two ages should have no intersection. So if we have one age, so obviously the condition holds. So we have 5 ages. So here we have 5 matching sets of size 1. Now, how about the size 2? If you take size 2, so you can see here E1 and E5. Look at E1 and E5. So there is no intersection between them. So the set consisting E1 and E5 is a matching set of size 2. And also E3, E4. There is no intersection between these two ages. So the matching set of size 2 is also the sets consisting E3 and E4. But you can see that there is no any more matching set of size 2, because if you take E1, E1 and E5 is the only matching set consisting E1, because you cannot choose E1 and E2 because they have intersection. Vertex V1 is an intersection between E1, E2, and also E1, E3. There is also intersection. E1, E4, they have intersection. So the only edge with E1 is E5, which is a matching set of size 2. So we have only two matching set of size 2. Now, do we have matching set of size 3? If you take any of 3 vertices, at least 2 of them has intersection. For example, E1, E5. If you put E2, where there is intersection. If you put E3 also. So the matching size of 2 is the biggest size, and we don't have any matching set of size bigger than 2. Now, how about the total number of matching sets? So we have one matching set of size 0, so that's 1. We have 5 matching set of size 1, so 1 plus 5, and 2 matching set of size 2. So the total number is 8. Now, by this example, let me give the definition of Usaha index. Suppose that gamma is a graph. So the total number of matchings of gamma is called Usaha index. So Usaha index is the total number of matching sets. So the Usaha index is usually denoted by Z of gamma. So Z of gamma is the Usaha index. So the Usaha index of gamma, as you can see here, is the number of matching sets. So if M of gamma is the set of all matchings of gamma, so the size of M of gamma is the total number of matchings, and here is called Usaha index. So that's the definition of Usaha index. So when we are going to compute Hosoya index. So we have to compute the set of all matchings of a graph. Now let me continue example in some other cases. So Hosoya index of graph gamma, which I have already showed you, we had 8 matching sets. So the set of matching sets consisting empty set, and we have 1, 2, 3, 4, 5 matching sets of size 1 and 2 matching sets of size 2. So the total number is 8. So Hosoya index of graph gamma is 8. Now, how about the path P3? Look at path P3. So here we have 2 edges, E1 and E2. Now, if we compute the set of all matching sets, so we have empty set as a matching set of size 0, and we have 2 matching set of size 1 consisting singleton sets of these 2 edges. And there is not anymore, because if you take 2 edges, you know that E1 and E2 has intersection vertex 2. So that's the only matching set. So we have 3 matching sets. That's the total number. So the Hosoya index is 3. Now, how about cycle C4? If you look the cycle C4, so the matching sets consisting empty sets, we have 4 edges, so we have 4 matching sets of size 1. Now, for matching sets of size 2, we have 2 distinct matching sets of size 2. You know, we have E1 and E3. There is no intersection between them. And similarly, E2, E4. So that's the only matching sets of size 2. So the total number of matching sets is 7. So the Hosoya index is that. And similarly for cycle C5, as you can see here, we have 5 vertices and 5 edges. So the matching sets consisting empty sets, we have 5 matching sets of size 1. Now for size 2, we have E1, E3. You know, E1, E3 is a matching set. E1, E4 is also matching set of size 2. Now E2, E4, and E2, E5. We have 2 more matching sets of size 2, and E3, E5. That's the only matching sets of size 2. We have 4 matching sets of size 2. So the total number of matching is 11. So the Hosoya index is 11. Now, how about the complete graph K4? Look at here, we have 4 vertices and we have 6 edges. So the matching sets consisting empty set as the matching set of size 0. We have 6 matching sets of size 1 because we have 6 edges, right? And we have 3 matching sets of size 2. You know, look at the graph. We have E1, E3. We have E2, E4. And also we have E5, E6. You know, E5 and E6 has no intersection. So the total number of matching sets is 10. So the Hosoya index is 10. Now, this is a formula for the matching sets of complete graph Kn for any n bigger than or equal to 2. So here is the formula, is the sum of n factorial over 2 to the power of k factorial times n minus 2k factorial. And the sum is taken over between k from 0 to integer part of n over 2. For example, if n is 4, as we have already found the Hosoya index for K4, if n is 4, so we have k is 0. If n is 4, so we have k is 0 until 2, right? So we have to compute this this amount for k is 0, k is 1, and k is 2. If k is 0, so and n is 4, we have 4 factorial is 24, and k is 0, 2 to the 0 is 1, 0 factorial is 1, 4 minus 0 factorial is 4 factorial. So it's 4 factorial over 4 factorial is 24 over 24. If k is 1, so again we have 4 factorial is 24 on the top, and the below is 2 to the 1 is 2, 1 factorial, and here is 4 minus 2 factorial is 2. So 2 times 2 is 4. And similarly for k is 2, so the total number is 1 plus 6 plus 3 is 10, which is exactly the same as we have already find the Hosoya index for K4 directly. So this is the general formula for the complete graph. Now, there are some results. The first results is that if we have two disjoint graphs, gamma 1 and gamma 2, so the Hosoya index of gamma 1 union gamma 2 is the multiplication of their Hosoya indexes. So by this theorem, we can extend our definition for Hosoya index not only for connected graph, but also for any graph, even the graph is disconnected. So if gamma is disconnected graph, and if we have k components, connected components, gamma 1, gamma 2, and gamma k, so the Hosoya index of gamma is the multiplication of the Hosoya index of each parts. All right. This is very nice formula, and by this theorem we can compute some more Hosoya index for some more graphs. So the theorem says that if gamma is a graph, and if V is an arbitrary vertex, right? So the Hosoya index of gamma is the Hosoya index of gamma minus V. Gamma minus V is that we have to remove vertex V. You know that if we remove vertex V from the graph, so any edges which intersects V will be removed too. So the Hosoya index of gamma is the Hosoya index of gamma minus V plus the sum of Hosoya index of gamma minus 2 vertices V and W, which W is is any of neighbors of V, right? So W is the W belongs to the set of all neighbors of V. This is a way to compute the Hosoya index of gamma through the Hosoya index of gamma minus V and the sum of gamma minus V and all neighbors of V. Let me give an example. So suppose that gamma is the following graph. So we have 4 vertices and we have 5 edges, right? So the edge between V1 and V2, it's E1, E2 is the edge between V2, V3, and so on. Now, let me take V2 as a vertex. So I'm going to just show this formula by choosing vertex V2. So if we take V2, how about gamma minus V2? You know, gamma minus V2, let me just show it a little bit. You know, you can see here, if we remove V2, so if we remove a vertex V2, so edges E1, E2, and E5 will be also removed from the graph. So gamma minus V2 is this graph, consisting of 2 edges, E3 and E4. Now, how about the neighbors of vertex V2? So V2 is adjacent to V1, V4, and V3. So we have three neighbors for V2. Now, we have to compute gamma minus V2 and neighbors. So gamma minus V2 and V1. If we remove V1 and V2, look at again here, V1 and V2. If we remove these 2 vertices, then we will have only edge E3. So we have V2 vertices, V3, V4, and edges E3. If we remove V2, 2 vertices, V2, V3, V2, V3, so we will have only edge E4. So we will have E4, right? And gamma minus V2, V4. If we remove V2 and V4, right? So all edges will be removed, and we will have also 2 singleton set, 2 isolated vertices, V1 and V3. Now, for each of them, we can compute the Hosoya index, right? So, for example, the Hosoya index, so this is the formula, the Hosoya index of graph gamma is the Hosoya index of gamma minus V2 plus the summation, the Hosoya index of gamma minus V2 and all neighbors of V2. So here we have the Hosoya index of gamma minus V2. Look at gamma minus V2. So what's the Hosoya index for this graph? So we have empty set. This is 1, and we have 2. We have 2 singleton sets consisting HE3 and HE4. Not anymore. We don't have any matching set of size bigger than 1. So we have 3 1 plus 2, 3 matching sets of the Hosoya index for gamma minus V2 is 3. Now, how about the Hosoya index for gamma minus the sets V2 and V1? We have only H. So we have empty set plus singleton set consisting E3. So we have two matching sets. So the Hosoya index for gamma minus the set V2 and V1 is 2. And similarly for the next one. And now for the gamma minus V2 and V3, we don't have any H. So the only matching set is 0. So the matching set for gamma, so we have 1 plus 2 for the Hosoya index of gamma minus V2, and we have 2 for the gamma minus V2, V1, and again 1 plus 1, 2 for gamma minus V2, V3, and 1 for gamma minus V2, V3. So here is 8. So the Hosoya index is 8, right? So this is a way to, of course, it's a short way to compute the Hosoya index through finding Hosoya index of gamma minus the vertex and sum of Hosoya index of gamma minus vertex with all neighbors. Here is another results by removing an edge, right? So if gamma is a graph and E, a small e, is an arbitrary edge, so the Hosoya index of gamma is the Hosoya index of gamma minus H E plus the Hosoya index of gamma minus the if you look HE, E consists of two vertices U and V. So that's the second part is the Hosoya index of gamma minus two vertices of HE. So gamma minus vertices U and V. Let me compute the previous example by removing H, right? So we take to put HE as E5. So E5 is or H, right? And E5 consisting two vertices, two end vertices, V2 and V4. So by the above formula, the Hosoya index of gamma is the Hosoya index of gamma minus E5, right? Plus the Hosoya index of gamma minus two vertices of E5 is V2 and V4. So the gamma minus E5, if we remove H E5, so we will get a cycle V1, V2, V3, and V4, right? And gamma minus V2, V4, if we remove V2 and V4, so all edges will be removed and we will get only two isolated vertices, V1, V3. Now, for the Hosoya index of gamma here is C4, and we have already defined C4. The Hosoya index of C4 was 7, and here we have two isolated vertices. So the Hosoya index is 1. That's only empty set as a matching set of size 0. So we will have 7 plus 1 is 8. That's the same as we find Hosoya index for this graph. Now let me give some applications of these two theorems. The first application of this theorem is to find the Hosoya index of complete graph Kn in terms of Hosoya index of some complete graph K, just a smaller size of Kn minus n minus 1 and Kn minus 2. Look at here. So suppose that Kn is complete graph consisting of n vertices, 1, 2, and n. You know, for complete graph Kn, we have n times n minus 1 over 2 edges. So if we put vertex I, right? So the Hosoya index, I'm using the first theorem about removing a vertex from the graph. So the Hosoya index of Kn is the Hosoya index of Kn minus vertex I plus the Hosoya index of Kn minus 2 vertices I and j, right? With j is an adjacent vertex to I. So the Hosoya index of Kn minus I, if we remove vertex I from Kn, we will get Kn minus 1. So this is the Hosoya index of Kn minus 1. And also, if you look Kn minus 2 vertices I and j, so if we remove 2 vertices I and j, we will get Kn minus 2. So we have the Hosoya index of Kn minus 2. But the total number is n minus 1 times, because I is adjacent to all other vertices in complete graph. And so the total number of vertices is n. So I is adjacent to n minus 1 vertices. So we have n minus 1 neighbor for I. So we have n minus 1 times the summation of z, the Hosoya index of Kn minus 2. So we will get this formula, the Hosoya index of Kn is the index of Kn minus 1 plus n minus 1 times of Hosoya index of Kn minus 2. Now, similar to Kn, we can also consider Pn, the path with n vertices. So here, if you put vertex 1 here, so the Hosoya index of Pn is the Hosoya index of Pn minus 1. So we remove vertex 1 from Pn plus the summation of Hosoya index of P1 minus. So the only neighbor for 1 is 2. So 1 has only 1 adjacent vertex. So it's the Hosoya index of Pn minus 1 plus the Hosoya index of Pn minus 2 vertices 1 and 2. So if we remove vertex 1 from Pn, we will get Pn minus 1. And if we remove vertices 1 and 2, we will get Pn minus 2. So we can get this formula that this Hosoya index of Pn is the Hosoya index of Pn minus 1 plus the Hosoya index of Pn minus 2. And also for cycle Cn, we can just find the Hosoya index of Cn in terms of the Hosoya index of paths Pn minus 1 and Pn minus 2. Because if you take a vertex 1, and if we remove vertex 1 here, so the Cn minus vertex 1, we will get Pn minus 1, right? And so 1 has two two adjacent vertices is 2 and n 2 and n, right? So the Hosoya index of Zn minus 2 vertices 1 and 2 plus the Hosoya index of Cn minus 2 vertices 1 and n. So if we remove 1 and 2 from Cn, we get Pn minus 2, and similarly for Cn minus 1 and n. So the formula which we can compute the Hosoya index of Cn in terms of the Hosoya index of past is the Hosoya index of Cn is the Hosoya index of Pn minus 1 plus 2 times of the Hosoya index of Pn minus 2. And if we use this formula for wheel, if you take the wheel with n plus 1 with n vertices, so we have vertex n as a center, and we have a cycle n minus 1. So n is adjacent to all vertices of Cn minus 1. Now, if we take vertex n, that's the center. So the wheel minus the center, we will get the cycle n minus 1. Now, if you take neighbors of n, so all other vertices are neighbors. So Wn minus 2 vertices n and 1, we will get Pn minus 2. So if we remove vertex n and vertex 1, we will get the path Pn minus 2. And similarly, if we remove n and 2, again, we will get another path Pn minus 2. And until n and n minus 1. So the Hosoya index of wheel Wn is the Hosoya index of cycle n minus 1 plus the n minus 1 times Hosoya index of Pn minus 2. So you can see that for computing the Hosoya index of wheel Wn is necessary to only find the Hosoya index of cycle Cn minus 1 and pass n minus 2. Now let me move just Hosoya index for some algebraic graphs. We start with non-commuting graph. So look at symmetric group S3, right? So if you look symmetric group S3, so we have 6 elements, identity, 3 cycles of length 2, 1, 2, 1, 3, 2, 3, and 2 cycles of length 3, 1, 2, 3, and 1, 3, 2. And we know the center of S3 is trivial. So the vertex set for non-commuting graph, as you remember, the vertex set for non-commuting graph of G is G minus the center. So here we have to remove center with only identity. So we will have 5 vertices for the non-commuting graph of S3, right? So the non-commuting graph of S3, as you can see, we have 5 vertices and we have 9 edges. So you can just consider a complete graph K5, which we remove 1 edge between 1, 2, 3, and 1, 3, 1, 2, 3, and 1, 3, 2. Okay. Now, the Hosoya index of a non-commuting graph of S3, so is the Hosoya index of K5 minus E. Now, by using the second theorem, which is a theorem about removing an edge from a graph, so we can see that the Hosoya index of K5 is the Husserl index of K5 minus HE, which is the non-commuting graph of S3, plus the Husserl index of K5 minus 2 end vertices of HE, which is 1, 2, 3, and 1, 3, 2. So K5 minus E, it's a non-commuting graph of S3, so that's the Husserl index of non-commuting graph S3, which we are looking to find it, plus the Husserl index of K3, because if we remove 1, 2, 3, and 1, 3, 2, so we'll get K3, so we will have 3 vertices, 1, 2, 3, 1, 2, 1, 3, 2, 3, and 3 edges, so that's the K3. Now, the Husserl index of gamma S3 is the Husserl index of K5 minus the Husserl index of K3. Now, we can use the previous results about we can use this formula. The Husserl index of Kn is the Husserl index of Kn minus 1 plus n minus 1 Husserl index of Kn minus 2. So if we use this formula, then and put the Husserl index for K3 and K4, which we have already defined, we will get 22. So the Husserl index of non-commuting graph of S3 is 22. Now let me give another example of algebraic graph, which is co-prime graph of S3. Again, if you look S3, we have 6 vertices. So the order of these 6 vertices are, we have identity of order 1, 1, 2, 1, 3, 2, 3, they have order 2, and 1, 2, 3, 1, 3, 2 is of order 3. So the co-prime graph, you remember, for co-prime graph, we will say that 2 vertices, x and y, they are adjacent if their orders are co-prime. So you can see that identity will adjacent to all other vertices. So 1, 2, 1, 3, and 2, 3, we don't have any edge between them because they have order 2 and they are not co-prime. And similarly, we don't have any edge between 1, 2, 3, and 1, 3, 2 because they have order 3. But we have edge between 1, 2, and 1, 2, 3, 1, 2, 1, 3, 2, because 2 and 3 are co-prime. Now, if we use the two formulas about removing edge and vertex, so if we take vertex E, so I'm using the first formula for removing a vertex. So the co-prime graph minus identity, that's the vertex identity. If we remove vertex identity, we will get the complete bipartite graph K3, 2. Now, we know that here we have 5 neighbors for vertex E. So the co-prime graph minus 2 vertices identity and 1, 2, we have K2, 2. And similarly, if we remove identity and 1, 3 and identity 2, 3, we have again K2, 2. And if we remove identity and 1, 2, 3, if we remove identity and 1, 2, 3, then we will get the star graph. So we have 1, 3, 2, which adjacent to 1, 2, 1, 3, 2, 3. And similarly, if we remove vertices identity and 1, 3, 2, we will have again a star graph K1, 3. So the Usaha index of co-prime graph of S3 is the Usaha index of K2, 3 plus 3 times Usaha index of K2, 2 and 2 times Usaha index of star graph K1, 3. Now, how about the Usaha index of K2, 3? If you look at K2, 3, again for computing the Usaha index of for complete bipartite graph K2, 3, we can remove, we can put vertex C, and if we remove vertex C from this graph, so the K2, 3 minus C, we will, if we remove vertex C, we will get K2, 2. And also we have 2 neighbors for C, so if we remove vertices C and A, we will have K1, 2, right? And also if we remove C and B, again, we will have K1, 2. So the Usaha index of K2, 3 is the Usaha index of K2, 2 plus 2 times the Usaha index of K1, 2. So by putting these amounts for the Usaha index of K2, 3, so the Usaha index of co-prime graph of S3 is the 4 times Usaha index of K2, 2 plus 2 times Usaha index of K1, 3 and 2 times Usaha index of K1, 2. And if we put, because K2, 2 is the C4 and the Usaha index is 7, and K1, 3, the Usaha index is 4, because if you take K1, 3, so the Usaha index is only empty set and 3 singleton set of edges. So we have 4. And similarly for K1, 2, we have 3. So the Usaha index of co-prime of S3 is 42. Okay, so up to now, we introduced 8 projects. So this is the project number 9. Project number 5 is to find Usaha index for the following algebraic graphs. The first one is for non-commuting graph of dihedral group of order 2 times n. So what's the Usaha index for this graph? You know, you have to find a formula in terms of n for the Usaha index of dihedral group. Now, how about the Usaha index for co-prime graph of 2 dihedral group of order 2 times p to the n, which p is a prime number, right? So dihedral group of order 2 times p to the n, co-prime graph of this graph. The third part is the conjugate graph of a finite group G. So in general, so what's the Usaha index for conjugate graph? And the last part is the Usaha index for non-normal graph of subgroup H consisting two elements, identity and B, of dihedral group of order n, of order 2 times n, which is a group generated by A and B, such that A to the n is B squared is identity and BAB is inverse. So this 4 parts is the project number 9. All right. So let me move to another topological index, which is Detour Index. So this is the topological index of number 5. So, first, let me remind you that this topological index introduced by two of mathematician by Amic and Trigonometric. They introduced this topological index in 1995. To introduce the Detour Index, we have to introduce first about Detour matrix. So let me define Detour matrix. Suppose that gamma is a connected graph with n vertices, 1, 2, 3, up to n. Now, if you take two vertices, I and j, we know that di and j is the distance between I and j, which is the shortest, the length of shortest path between I and j. Now, we denote d star of I and j. Here is the length of longest path between two vertices I and j. You know, if you take two vertices, sometimes we have different paths. So the shortest, the length of shortest path is the distance between I and j, and the length of longest path is the d star I and j. So the Detour matrix of graph gamma we may denote by capital delta, and is defined as the following. So the Detour matrix of graph gamma is n times n matrix. So we have vertices, n vertices as rows and columns. And if you take two vertices on I and j, right? So the entry I and j for the Detour matrix can be defined as the d star ij is the length of longest path between I and j if I is not equal j, and if I is j on the diagonal, we will have 0. This is a Detour matrix. Let me compute Detour matrix for some graph. If you take for complete graph, we have 5 vertices, and so, you know, any of 2 vertices, they have edge between them. Now, the distance between I and j, right? The I and j, the distance between I and j is the length of shortest path, because I and j, they are adjacent. So the shortest path is 1 because there is only h between them. So di and j is 1. Now d star I and j. Look at, for example, 1 and 2. So the shortest path between 1 and 2 is 1. Now how about the longest path? You know, the longest path is that we can go from 1 to 5, 5 to 4, 4 to 3, 3 to 2. This is the longest path. The length of longest path is 4. So the Detour index of the Detour matrix of K5 is on the diagonal we have 0, and all other interest is 4, because if you take any of two distinct vertices I and j, the length of longest path is 4. And you can see that this is 4 times of the matrix J 4 times 4. This is 4 times 4 matrix, which all entries are 1 minus the identity. Now, take graph gamma as the following graph. Here we have 8 vertices, right? 1, 2, 3, 4, 5, 6, 7, and 8. Now, how about the detour index of this graph, detour matrix? So the detour matrix of graph gamma is 8 times 8 matrix. Now look at row number 1. So if you take the first row, so the longest path between 1 and 1 here is 0 by definition. The longest path between 1 and 2, the shortest path between 1 and 2 is 2, but the longest path is, we can go from 1 to 8, 8 to 7, 7 to 6, to 5, to 4, to 3, to 2. So this is a path of length 7. So the longest path between 1 and 2 is 7. The longest path between 1 and 3 is 6. The longest path between 1 and 4 is 6, so and so on. So here is the detour matrix of graph gamma. You can see that the detour matrix for complete graph Kn, as we have already defined for K5, was 4 times the J 4 times 4 minus identity. Now, in general, we can say that the detour matrix of Kn is n minus 1 times of matrix J m n times m minus the identity matrix n times n. You know that here the longest path between any of two vertices in Kn is n minus 1. For example, for K5, this is the detour matrix, right? And how about for Cn, for cycles of length n? Here is the detour matrix for C4, right? For example, from vertex 1 and 2. 1 and 2, the longest path is 3, because we can go from 1 to 4, 4 to 3, 3 to 2. And also here is the detour matrix for C5 and detour matrix for C6. You can see that in a cycle, if you take any two distinct vertices I and j, so the length of longest path between two vertices I and j is the maximum of absolute values of I minus j and n minus the absolute values of I minus j. So we have two cases for the detour matrix of Cn. If n is even, here is the detour matrix. And if n is odd, we will have this matrix, both matrices of n times n, matrix with a little bit different in some entries. Now, you can see that sometimes detour matrix and distance matrix are the same if we have a tree, tree is a connected graph with no cycle. So if we have a tree, and if you take two distinct, arbitrary distinct vertices I and j, so from vertex I to j, we have a unique path in a tree. Since we have only one path between vertex I and vertex j, so the shortest path and longest path are coincide. So we have only one path. So it means that the distance between I and j, so d of I and j, as a shortest path and the longest path, they have the same value. So the Detour Index, the Detour matrix, and the distance matrix are equal. So as a corollary, we can see that for paths Pn, Detour matrix and distance matrix are the same because Pn is a tree. So you can see that if you look P3, this is the Detour matrix, which is the same as distance matrix. That's the Detour matrix for P3 and P4. Now, how about the Detour matrix for complete bipartite graph KMN? So look at K24 as an example. Complete bipartite graph K24. We have two parts of vertices. The first part consisting two vertices, 1 and 2, and the second part consisting four vertices, 3, 4, 5, and 6. Now, the length of longest path between 1 and 3, between 1 and 3, between 1 and 3, the shortest, the length of shortest path is 1. But how about the longest path? So we can start from 1, for example, to 5, 5 to 2, 2 to 3. So we have a path of length 3 as the longest path. So if we have two vertices, first from part 1 and second from the second part, so the length of longest path is 3. Now, how about between two vertices in the first part, 1 and 2? For between 1 and 2, the longest path is going from 1, for example, to 5, 5 to 2. So is 2. From the second part, 3 and 4. For 3 and 4, we have we have longest path of length 4 because we can start from 3 to 1, 1 to 5, 5 to 4, 5 to 2, 2 to 3. So between 3 and 4, we have a longest path of length 4. So here is the Detour matrix for complete graph K23. So now, in general, for the complete graph of K, M, and N, so if we have M vertices in the first part and N vertices in the second part, we can see that the length of the longest path between any of two vertices in the in the first part. So the length of longest path between, for example, A1, A2 is equal to between A1, A3, A1, A4, A2, A3. So the D star A AA and AJ is equal to D star A1 and AM. And similarly, for the second, if we have two vertices in the second part, so the lengths of longest paths are the same, right? And if we have so what we have to see is to compute the length of longest path between any of two. What we have to do if we take two arbitrary vertices, so we have three possibilities. Two vertices are in the first part or the second part, or one in the first part and the second in the second part. So here is the length of longest path between, for example, A1 and AM. Right? We have two cases in terms of M minus 1 is less than or equal to N or bigger than N. And that's the length of longest path between B1, BN and A1, AN. So if we put them, then we can get the detour matrix of complete bipartite graph KMN with this matrix. Now, by defining the detour matrix, we can define the detour index. So suppose that gamma is a graph with n vertices, and if delta of gamma is the detour matrix of gamma, then the detour index of graph gamma can be defined as the following. So we can add all entries in the detour matrix, right, and divide by 2. So let me say again, so if we have detour matrix, so we have all entries in the first row, second row, third row. So we have to add all values of entries of this matrix and then divide by 2. That's the detour index of gamma. For complete graph Kn, so as we have already shown, so the detour matrix is n minus 1 times Jn times n minus identity In times n. So the detour matrix, the detour index of graph gamma, graph Kn, is the sum of all entries divided by 2. So it's the half of the sum of all entries. And if we have all entries here, you can see that Jn minus 1 minus In times n is the adjacency matrix. So we have n minus 1 over 2, the sum of all entries in the adjacency matrix of Kn, right? And if you look at the sum of all entries in the adjacency matrix is 2 times of the number of edges. So we can get the formula n times n minus 1 over 2, n minus 1 square over 2 as the detour index of complete graph Kn. And you can see that if n is 4, then the detour index is 18. Let me give some results about the detour matrix, the detour index. So the detour index of path Pn is n cubed minus n over 6, the Detour Index of cycle Cn. In terms of n is even or odd, we have 2 cases, and also Detour Index for the complete bipartite graph KMN. Also, we have 2 cases, and here is a lower bound and upper bound for the Detour Index of any connected graph with at least 3 vertices. Okay, now let me give project number 10. So, similar to the previous index, so the first part is to find Detour matrix and Detour index for non-commuting graph of dihedral group of order 2 times n. And the second part is just again Detour matrix and Detour index for non-coprime graph of dihedral group. Project number 11 is if we have 2 graphs, gamma 1 and gamma 2. So what we can say about the Detour index of these 3 products? That's a Cartesian product between graph gamma 1 and gamma 2, tensor product of this group of these 2 graphs, and also coronal products of graph gamma 1 and gamma 2. Okay, now I'm going to define the index number 6. It's the Heroin index. So, suppose that gamma is a connected graph. So, if we have vertex set consisting n vertices 1 to up to n, and if dij is the distance between 2 vertices, 2 distinct vertices I and j, so as we have already introduced, the distance matrix of graph gamma is n times n matrix, which are index set columns and rows by these n vertices. And if you take 2 vertices I and j, so the entries dij is the distance between I and j, right? So here is the distance matrix, which I have already defined. Now, let me introduce another matrix related to distance matrix. We denote it by RD. So RDIJ, the RD is n times n matrix, and the entries ij of this matrix can be defined in 2 cases. If I, the distance between I and j is 0 when I equal to j. So if I equal to j, so the entries I and j is 0, and if the entries I and j is not 0, right? So the dij, we have 2 cases because the graph is connected. When the graph is connected, if you take this, if you take 2 arbitrary vertices, we will have a pass, at least a pass between them. So the distance is not 0. The distance between I and j is 0 whenever I is equal to j. So if I is not equal to j, so the entry ij of this matrix is 1 over d, I, and j, right? So 1 over distance between vertices I and j. That's the inverse of dij. Let me introduce more about this matrix and give some examples. Look at this graph. We have 5 vertices, right? So the distance of this matrix is a 5 times 5 matrix. Look at here, the first row. So 1 and 1 is 0. 1 and 2, the distance between 1 and 2, because 1 and 2 are adjacent, so the distance is 1. 1 and 3, the distance is 3. 1 and 4, 1 and 4, distance is 3, because you have to go from 1 to 2, 2 to 3, 3 to 4. And between the distance between 1 and 5 is again 3. So the shortest path is going from 1 to 2, 2 to 3, 3 to 5. And similarly, we can put all entries for the distance matrix. Now, the new matrix RD of gamma is the, so we put 0 on the diagonal, so it's the same. And we have to put the inverse of all non-zero entries. So the inverse of 1 is 1, inverse of 2 is 1 over 2, inverse of 3 is 1 over 3, inverse of 3, 1 over 3, so on and so on. So every entries, non-zero entries of RD is the inverse of entries, the same entries in distance matrix of graph gamma. If we look the distance matrix of complete graph Kn, you know that in graph Kn all vertices are adjacent. So the distance matrix of graph Kn is n times n matrix with all entries are 1 except diagonal, which are 0. And you can see that the new matrix RD of graph Kn is the same, because the inverse of 1 is 1. So we can see that the RD of Kn is the distance matrix of Kn. Now, how about cycle C5? You know that the distance matrix of C5 is here. Look at here, just show the first entry, the first row. So 1 and 1 is 0. The distance between 1 and 2 is 1. 1 and 3 is 2. 1 and 4 again is 2, because you know from 1 to 4 we have 2 paths. From 1, 2, 3, 4, or 1, 5, 4. The shortest path is 2. And 1 to 5 is 1. So that's the distance matrix. Now, the RD of C5 is the inverse of any entries except diagonal. So that's the, you know, I put inverse of any of just similar entries in distance matrix except on the diagonal, which are 0. Now, by this matrix, now I'm going to define the Heroin index of graph gamma. So if gamma is a graph and the vertex set is 1 to up to n, so the Heroin index of gamma is denoted by h of gamma and defined as the following. So we have to find the sum of all entries of the new matrix RD and divide by 2. So that's the Heroin index. And you know, Harari is one of famous mathematician in graph theory, and he introduced several topological indexes, and the Harari index first introduced by Prof. 6 in 1993, and because of the honor of 17th birthday of Professor Frank Harari, so they put name Harari for this index, this topological index. So Harari index we introduced for connected graph, but if the graph is connected, then we can see that the Harari index is the sum of Harari indexes of all, the sum of Harari index of all parts. Now, how about the Harari index of Kn? So the Harari index of Kn, as we have already shown, the RD matrix of this graph is, you know, for the, you know that the for Kn, the distance matrix and RD matrix are the same. So the sum of all entries of RD matrix is the, you know, if for example, if you take I is 1, so the sum of j is 1 to n, and 1 over dij is 1, the sum of them is the degree of I. So the Harari index of Kn is n times n minus 1 over 2, which is the number of edges of completed graph Kn. For the Harari index of Pn, for Pn, you can see that, for example, for P3, P4, and P5, here is the distance matrix for P3 and RD matrix. So the Harari index for P3, the sum of all, you know, the sum of all entries divided by 2. So we have 0 plus 1 plus 1 over 2 plus 1 plus 0 plus 1 plus 1 over 2 plus 1 plus 0 divided by 2. So it's 5 over 2. For the P4, the Harari index is 13 over 3. For P5 is 29 over 4. Here is the formula for the Harari index of Pn in general. So is the sum of n minus k over k for k between 1 and n minus 1. You can see that here. For example, if n is 3, you can get again the same values as before, 5 over 2. For n is 4 is 13 over 3, and n is 5 is 29 over 4. Here is a lower bound and upper bound for the Harari index of a connected graph with at least 2 vertices. So here is the lower one, and that the upper one. And you know, we have equality on the left-hand side if the graph is Pn, and similarly we have equality on the right-hand side if the graph is complete graph Kn. So here is the Harari index for a cycle of length n in terms of n is odd or even. here are some examples. And this is a very important lemma. You know that if gamma is a connected graph with n vertices, we may denote gamma just a small gamma of graph gamma and k is the number of vertex pairs of gamma that are at distance k, right? So here, you know that if you take any of two vertices, so they have a special distance. If we just order all pairs of distance 1, distance 2, distance 3, and we can see that it will goes to utmost diameter, the longest path between two vertices. And Heroin index can be computed by this just formula. And if we use this formula, then we can see that if k is 1, so the gamma of graph gamma and 1 is the number of pairs, number of vertex pairs of adjacent vertices. So that's the number of adjacent vertices, and you can see that is the 2 times of number of edges. So by this lemma, we can see that the Heroin index of gamma for a connected graph gamma is the number of edges plus the sum of this amount, the 1 over the distance between Vi and Vj, but here Vi and Vj are not adjacent. It's a non-adjacent vertex pairs. As an example, again, if you look at the complete graph S3, so here is the graph, and you can see that you know the number of adjacent we have. You can see number of edges is 9, and we have only 2 non-adjacent vertices. So this is the number of edges plus 1 over the distance between 1, 2, 3, and 1, 3, 2. And you know that the distance between 1, 2, 3, and 1, 3, 2 is 2, because we should have 1, 2, 3, for example, 2, 1, 2, and 1, 2, 2, 1, 3, 2. So the Heroin index is 19 over 2. Here are some results about the Heroin index for complete bipartite graph, KMN, and in general case for complete k-partite graphs. Right, this is the formula for the Heroin index, and also here is a lower bound and upper bound for the Heroin index with at least 2 vertices and m edges. And if the graph is triangle free and quadrangle free, so here is an upper bound for the Heroin index of gamma in terms of the number of vertices and the number of edges. And if the graph gamma is connected and has at least 5 vertices, and if the complement of gamma, the complement graph of gamma is also connected and diameter 2, so here is the lower bound for the Heroin index of gamma plus the Heroin index of complement of gamma. And we have equality if the graph is past Pn. And here also a lower bound and upper bound for the Heroin index of gamma plus the Heroin index of gamma bar. Now, let me move to algebraic graph. So I'm going to state the Heroin index of non-commuting graph of dihedral group. So look at dihedral group of order 8, right? So the center contains two elements, identity and A square. So we have 6 vertices, and here is the non-commuting graph of D8. So here is the distance matrix, and here is the RD matrix, and the Heroin index of non-commuting graph of D8 is 27/2. Now, similarly for dihedral group of order 10, so here is non-commuting graph. We have 9 vertices. So here is the distance matrix and RD matrix and the Heroin index for the non-commuting graph of dihedral group of order 10, which is 33. Now, it's interesting to find the general formula for Heroin index of non-commuting graph of order 2 times n. And here is the result for the Heroin. It's in the paper with myself and 2 co-authors. That's the Heroin index for the non-commuting graph of dihedral group of order 2 times n, when n is even or n is odd. You can see that, for example, if you put n is 4 and 5, you will get exactly the amount for the Heroin index of non-commuting graph of D8 and D10, which is 27/2 and 32, which we have already found in a direct way. Now, let me give project number 12. Project number 12 is the to find Heroin index for Cartesian product of 2 graphs and also tensor product and coronal products. The next topological index is Balaban Index. Balaban Index defined as the following: if gamma is a connected graph and if we have n vertices and m edges, then if we denote duv as the distance between any 2 vertices u and v. So first we may denote w of u. W of u is the sum of duv for any v in the vertex set gamma. So w of u is the sum of distance, sum of all distances from u to all other vertices. So from u to all other vertices, we have to find the distance, and the sum of these distances is the w of u. Now, the Balaban index defined as the following: they denote the Balaban index by capital J. So the Balaban index of gamma, J of gamma, is m over m minus 1 plus 2. M is the number of edges and n is the number of vertices. Summation of 1 over the square root of w of u, w of v, which u and v is 2 adjacent vertices. So for any edge in graph gamma, we have to consider 2 n vertices u and v. The sum of these values is the Balaban index, and Balaban index introduced in 1982 by Alexandru T. Balaban, and later, just in 2011, Deng introduce some Balaban index. Some Balaban index, we have the same formula, but here here on the Balaban index, this is the multiplication, is the square root of multiplication of WU and WV, but in some index is the sum of the square root of sum of WU and WV. So, for example, if you take K3, so we have 3 vertices and we have 3 edges. So N is 3 and M, the number of edges is 3. Now, look at here. How about W of, for example, U? W of U, so we have to add the distance between U and any other vertices. So distance between U and V is 1, U and X is 1, 1 plus 1 is 2. So W of U, W of V, and W of X is 2. So here we have 3 vertices and 3 edges. So we have 3 over 3 minus 3 plus 2. You know, here we have 3 edges between U and V, U and X, and V and X. And as I mentioned, W of U and V and X is 2. So the Balaban index for K3, we have 9 over 4. Similarly, for K4, we have 4 vertices and we have 6 edges. So for any of 6 edges, for example, edges between x1 and x3, we have to find wx1 and wx3 and multiplication of them and a square root of them, right? So the Balaban index for K4, because the values for x1, x2, x3, and x4 are the same. So, and since we have 6 edges, so the Balaban index is for K4 is 3. And this is the formula in a general case for Kn is n cubed minus n squared over 2 times n squared minus 3 times n plus 4. And the proof comes from the formula that we have n vertices and we have n times n minus 1 over 2 edges. And W of U is the sum of all distances from U to all other vertices. We have n minus 1. And here you can see that the Balaban index of Kn is this is the number of edges, the n times n minus 1 over 2, and n is the number of vertices, and you can see we can get that above formula. Here is another example for C4. For C4, we have 4 edges, and you can see we find the Balaban index for C4. Here is some research problems for Cn. It's interesting to find a formula for Cn and for Pn, and also compare the Balaban index and some Balaban index, G of gamma and Sg of gamma as the some research problem. Now, project number 13 is to find the Balaban index and some Balaban index for co-prime graph of dihedral group of 2 times n. You know, mostly I concentrate on non-commuting graph or co-prime graph of dihedral group because it's not so difficult to compute coprime graph and also non-commuting graph. Right, so let me just introduce some more topological indexes for not all details, just introducing the formula, the definition, and also the just one example. The number of 8 of topological index is Strada index. Strada index comes from the graph and from the adjacency matrix of gamma and eigenvalues of adjacency matrix. So if lambda 1, lambda 2, and lambda n are all eigenvalues of adjacency matrix of graph gamma, then the Strada index of gamma defined as the sum of these values. So that's the exponent e to the lambda I from I between 1 and n. For example, for Kn, as we have already shown, Kn has eigenvalue -1 with multiplicity n-1 and n-1 with multiplicity 1. So that's the Strada index of Kn, which is n-1 times E inverse e to the -1 plus e to the n-1. The another topological index, which is Rundic index. Rundic index is that if gamma is a connected graph, right? So the Rundic index of gamma is the sum of 1 over the square root of multiplication of degree u times degree v, which uv is an h in gamma. So for any h in a graph gamma, we have to compute the degrees of n vertices of this h and put on the square root. And the sum of them is the Rundic index of gamma. Again, for example, if you take complete graph Kn, we know that the degree of any vertex is n-1 because the graph is regular. So the Rundic index of graph Kn is because we know that the number of edges is n times n-1 over 2. This is the number of edges. And here is that the degree of any ends of n vertices of any h in Kn, we have n-1 times n-1, so the Rundic index is n over 2. Now, another index is Gottman index. Gottman index is the graph, if you take a connected graph, right? So the Gottman index of graph gamma is the multiplication. If you take any pair of vertices, right? Pair u and v, two vertices. So if we compute the multiplication of degree of u, degree of v, and distance of u and v, if we multiplication of 3 values and the sum of this multiplication for all pairs of vertices, that's the Gottman index. For example, if you take Kn, so you can see that the degree of any vertex is n-1, and the distance is 1, and the number of pairs in graph, complete graph is equal to the number of edges because any 2 vertices are adjacent. So here is the Gottman index, and it's n times n-1 cube over 2. And the H winner index, we have already introduced the winner index. This is the H winner index. First, you can see the the distance between any two edges. So if we have two edges, u, v, and x, y. So the distance between any of two edges is the minimum distance between the end vertices of the first edge. So is and the second end vertices of the second edge. So the distance between u and x, u and y, v and x, and v and y. So the minimum of this distance is the minimum is the distance between any two edges. So the edge winner index of gamma can be defined as the just sum of any distance of any pairs of edges. So if E and F are two edges, so the distance between any of two edges and the sum of all sum of all pairs of edges is the H winner index of gamma. So if you take for C4, you know that here we have four edges. So the distance between, for example, H E1 and E2 is 0, E1 and E4 is 0 because they have intersection, and the distance if from 1 to 1 is 0. And the distance between E1 and E3 is 1. And similarly for E2, E3, E2, E4, and E3, E4. So the sum of all distances between any of two edges here we find, and it's equal to 2. The last topological indexes is hyperwinner index. Hyperwinner index they denote by WW of gamma, and that's defined as the following way. To if you consider a pair u and v of vertices, so if you add the distance between u and v and plus the square of distance u and v, if you add these two amounts and just sum of this amount for all pairs of vertices, that's the hyperwinner index. For example, for complete graph Kn, you can see that the hyperwinner index is n times n minus 1. You know, there are many other topological indexes, so I just introduce some of them for this and the rest for a little bit details. So here is 12 topological indexes. Thank you very much. So I finished this series of lectures about probability, about algebraic graphs, about matrices associated to graph, and the last part is topological indexes. I suggest, if I have possibility in the next time, to explain about some polynomials associated to a graph. And that's very interesting, because if you associate a polynomial to a graph, so we have many things to find about this polynomial. For example, finding this polynomial, roots of this polynomial, and so on. So this is my suggestion for the next time, inshallah. Thank you very much, and sorry that I take more time from you, and I hope that you you enjoyed from this series of lectures. And also I'm very grateful for all organizers of this lectures, and for the project which I introduced, you may also manage about the young graph theorists or algebraic or group theorists who are interested to join to this work. So I'm available, and you can contact me through WhatsApp or through my email. And I hope that this series of lectures will provide a situation to start some more joint work with colleagues in UGM or your students, and also for master or PhD students. Thank you very much indeed.
Okay, thank you very much, Professor Ahmad Erfanian, for the very meaningful and enjoyable lectures. And this is the last one from 7 lecture series. And actually, for the follow-up for this lecture series, we are making some smaller groups because as you see, when every week we have lecture, then we need some time to understand everything, right? So we make smaller groups to discuss further for the lecture, and also especially for the projects, because for the projects, of course, we need more time for trying to solve together, and especially for our students also. And before, I think maybe we will have some discussion, maybe any question or comments for the last one, maybe from Professor Indah, or maybe from Dr. Yeni, or the other one.
From me, for today,
Okay.
I have no question, Professor Erfanian. I just would like to thank you for your lecture. We have so many materials to explore and so on. We thank you very much for your willingness to give us some lessons and also provide us with some projects and so on. And here we have some students. I think some of them will be ready to maybe to just one or several from the problem you give us. And for instance, Agista here, Mas Agista, you will start your thesis in next semester. I think you have many problems to choose from. So I hope everything will be smooth in the future. If we have some like problem or something, we will contact you, Professor, and I hope you will not mind to give further discussion with us. Thank you very much, Professor Erfanian.
Okay, thank you very much from me too. So it's my pleasure to have some joint work with you and Prof. Inda and all other colleagues, Prof. Yoni. So I have many friends in UGM, so I'm very happy to have some joint work with all of you. Thank you very much.
Okay.
Thank you again from me to Professor Erfanian. I have some small question, Prof. Erfanian, about the motivation when you introduce USIIMA Index. You said that the motivation comes from chemistry. And
yes.
Is there some advantage for them, for chemists, if they know the USIIMA Index?
I think yes. You know, if you would like to get more details about just a chemical view of these topological indexes, there are some books and there are some journals about some application of these topological indexes in chemistry. So if you like, I can introduce some of them. Of course, it's in chemistry, and many things in chemistry which may be difficult for us to understand because we have to improve our knowledge on chemistry, and we don't have more time to know more about the chemistry. But there are some journals, there are many papers, and also some books about application of topological indexes in chemistry. Because as I mentioned, they are mostly coming from chemistry. So it means that the motivation actually comes from the chemistry, because in chemistry, they are important. But here we are talking about a graph, which are some non-graph, but the graph may be coming from the a special molecule or something from chemistry. So if you replace our graph by some important graphs in chemistry, so it means that you find some results about this amount in chemistry, which are actually they have more application in chemistry. Yes, I will send a book or maybe some links of journals for more details about these topological indexes. Yes, I will do it.
Thank you, Prof. Erfanian. And also as follow-up from these activities, as who has said that we will continue with the discussion with our students and also with you, maybe
yes,
email or maybe online like this.
Yes,
sometimes.
Yes. Just you may know that I have some joint project with Dr. Yeni, and sometimes we have online discussion with her and her students. So you are also welcome to maybe another project, and I will be available to have some joint work with you. And probably maybe it's of course depends on the situation of coronavirus. Maybe it's possible for me as before to visit your university maybe for 1 or 2 weeks sometimes. So it depends on the situation. Yes. Anyway, I'm very happy to have some joint research work with you and other your colleagues in UGM. Yes, of course.
Thank you very much. I think it's enough, Mauha.
I think it should be enough for today. And again, please give him a big applause for sharing from the first lecture until the last one. And thank you very much again to Professor Erfanian. And hope for the future we also can still make a good collaboration, especially like what Dr. Yeni said before, and also Professor Indah said before. And I think that's all for the event, for the whole lecture series. And in the first lecture, I think I mentioned about the A certificate and also the requirements. And only me and then Dr. Yeni and Professor Anand usually who are asking. So I think we only give for some people, not for all, because we try to see for the active participation. And again, thank you very much for all of you for joining the lecture series, and see you in the next event. Okay, thank you very much, everyone. Thank you.
Okay.
Thank you very much.
Thank you very much. All right. All right then. Hope to meet you again.
I hope,
Not virtually, but actually face to face in your university. Inshallah. Inshallah. Thank you very much indeed. Bye bye then. Bye.
Bye bye.
Bye bye then. Bye.